Which of the following would react the fastest in a nucleophilic aromatic substitution reaction? And this can also be abbreviated SnAr, or as I like to call it, SnAr. So if we're looking at a SnAr reaction, we need to know the criteria for this. So this is completely different than the reactions that we've been studying. We've been looking at EAS reactions, the electrophilic aromatic substitution reactions. And in those reactions, what we saw was that the ring itself, the benzene ring, was the nucleophile. So anything that gave extra electrons to the nucleophile made it react better. So EAS reactions are going to react faster when you have electron donating groups. So that's an electrophilic aromatic substitution. So it stands to reason that a nucleophilic aromatic substitution would have the opposite electronic requirements. So for your SnAr reaction, it's actually going to go better if you have electron withdrawing groups. Right? And so that information might be enough to get you to the right answer here, but I want to go through the full set of criteria for a nucleophilic aromatic substitution. So not only do you need to have electron withdrawing groups, we need some really specific things. So you need to have, it's a substitution, and you're not replacing a hydrogen this time, you're replacing a leaving group. So you need to have a leaving group. So this is one criteria, that the ring has to have a leaving group. And that leaving group is typically a halogen. In this case, we actually see we are using all examples with fluorine, which can actually be a leaving group in a SnAr reaction, which is not what we're used to seeing. That doesn't work with SN1 or SN2. So it can be a halogen. Okay. You need powerful electron withdrawing groups. So powerful, electron withdrawing groups, and that's typically nitro. And I'll show you an example with a mechanism so you can see why the nitro group actually works really, really well for this. And also it'll show you this next requirement, which is that those electron withdrawing groups need to be at the ortho and para positions, and or ortho, para. Okay, so those are the requirements. So seeing that, we might very quickly pick out D here. We've got our leaving group, our halogen, and we've got the nitros that are ortho and para. Right, so you have a leaving group, and we have these ortho-para electron withdrawing groups. So that's what makes this a really good substrate. Okay, but let's take a look at the reaction mechanism for a SnAr reaction so we can get an idea of why we have these requirements. Okay, so I am going to draw a mechanism. The only other good substrate for a SnAr would be B. This would also work. You've got a para-nitro group. So I think I'll draw the mechanism with B for simplicity. So in terms of what we can substitute for our leaving group, it just has to be a nucleophile that is a stronger base than the leaving group. So let's just pick an example. So I'm going to use B. So I'm not saying this is the fastest. It just is going to kind of simplify my drawing here because I only have to draw one nitro group getting involved. Okay. So this is just an example. So this is an example SnAr reaction. So like we said, the nucleophile we're adding just has to be a stronger base than what's leaving. So let's use hydroxide. So let's say we have a hydroxide ion. The way that this works is it is going to first add to the benzene ring. So in a nucleophilic aromatic substitution, you have this pathway. You're going to first add to the ring, so you're going to have addition. And then you're going to have elimination to make it back to an aromatic ring. So let me show you what I mean. So after this oxygen adds, we can't just break the bond SN2 style. It's because this is an sp2 hybridized carbon atom. What's going to happen is that's going to push electrons onto the ring. Right, so we no longer have a pi bond here, and we've also added that OH, and we've put some electrons into the ring. And so here's where I want to draw a resonance structure that shows you why this nitro group is important and why it has to be at the para or ortho positions. If you don't have your nitro group at the para or ortho positions, it can't participate in resonance as I'm about to draw. So this can stabilize that negative charge because we can actually push the electrons all the way through to the oxygen of the nitro group. So we can do that. And that's how that nitro group is participating and helping to stabilize this anion. All right, so this was the addition portion showing the resonance stabilization of that anion. We want to get back to having an aromatic ring, so now we're going to do the second half of this reaction, which is elimination. So we need to push electrons back through, and we can push from either one of these oxygens here and kick off our leaving group. So we can push back through here, here. So now we're putting another pi bond in the ring, moving this pi bond, and kicking off the leaving group. And so that'll give you your nucleophilic aromatic substitution product. Okay, so I'm going to put some square brackets around my resonance structures, and then we'll get to the product here. So we replace that fluoride with the OH. Okay, and the only other thing I think to note here is that this leaving group, another requirement of this reaction, that this needs to be a weaker base than the incoming nucleophile.